Hello, glad to see you in another video. Today, we are going to write a PLC program for small industrial process where we are going to use counters and clock memory bits. In fact, today's lesson stands as an application to the two previous videos about counters and clock memory bits. Here is shown the system and its corresponding inputs and outputs. Let's see how the system works. Prior to that, two fundamental principles a fresh PLC programmer needs to master, which are understanding well how the system works and its sequencing. Well, the motor is activated by a single press on the start push button. The motor makes the conveyor roll. The green indicator light turns on when the motor is active. The first sensor detects the small boxes and increments a count-up counter for each detected box. When the counter accumulates a certain number of boxes, the blue light turns on in flashing mode and the motor stops for a period of time before it runs again. When the green box is full, it's removed and the second sensor detects the operation and decrements a countdown counter. When the countdown counter accumulates a certain number, it stops the motor until it's run by the start push button. The stop push button stops the motor at any time. As usual, it's appropriate to identify the inputs and outputs before to start programming. Here they are. As usual, we head first over PLC tags to enter the system inputs and outputs. This allows us to think through the rest of the code more easily. Well, as we use a modular PLC, we need to add inputs and outputs modules. We get into the device configuration, we pick from the catalog one input module and output one, then we select the CPU and we head over properties to enable the use of clock memory bit since we need to activate a process output in flashing mode. We modify the byte number to 100 to avoid memory overlapping. This means using the same memory bit for several different variables, resulting in the program not working properly. We go back to the main OB to start programming. We try to follow the sequences of the process. We use an SR flip-flop for motor start and stop. We start first the code that runs the motor, then we go back to the conditions that stops the motor as we progress in the program. So, in the set we put the start push button to turn on both the motor and the green indicator light. We assign for each their addresses. For the sake of organization, it is regarded as appropriate to name the role of each network while programming. Good, we move now to the sequence of counting the small boxes. We use a count-up counter. We head over the counters folder and use, for example, an old version one and see how it works. As we can see, the Step 7 counters are arranged in their own folder under the name Legacy. We give the counter its address. The letter C means the space memory for counters. The counter increments at each positive edge detected in the CU input, so we drag an open contact and assign it with sensor 1. Better we use the positive edge when we deal with sensors, as this prevents the process from damages in case of sensors issues or inconvenience. The CV shows the current counter value as it increments. It is an integer number. Integers are represented by a word data size which is 16 bits. We choose, for example, the 4th memory byte. So, the counters increments each time the sensor detects a box on the conveyor. We name the network, then we move to the rest of the code. The next sequence consists in turning on the blue indicator light in flashing mode and stops the motor for a period of time when the sensor detects a certain number of boxes. We will therefore need in the first an equal operation comparator. The comparator will have as variable from one hand the counter's current value and from the other hand the number of boxes required by the process to activate the sequence. We put, for example, 5. This means only when the number of the small boxes reaches 5 the instruction lets the signal pass. As we said, first the comparator activates the blue indicator light in flashing mode. So we drag a coil and assign it with the indicator light, and to make it flash, we add an open contact bearing as address a clock memory bit. The comparator is also the condition to activate the timer that will turn off the motor temporarily. So we open a new branch just after the comparator and add the right timer. We pick an old version one, supposing that we know how it works. For more information about timers and counters, check the previous videos. Well, we assign the timer its address and the time period. Obviously, the values we used for the counters and the timer serve only the simulation purpose, they do not reflect the reality of the process. We move now to the next sequence, which is counting the big boxes removed. These are detected by the second sensor. We can think of a countdown counter. This time, we use a data block counter. With the data block counters, its address shows up directly over the counter. Well, in the CD input we put the second sensor. As we already said, better we use a positive edge. The counter decrements at each positive edge detected, and the output will turn on when the current value is equal or less than 0. In this program, we need the output to turn off the motor when a certain number of big boxes are removed. Well, we drag a coil and assign it with a memory bit address. This way we retrieve the state of the output. We can therefore use it anywhere in the program, in our case turning off the motor. As to the current value, it's optional in this program, still we give it an address for a better simulation of the program. In the previous counter the CV address was MW4, that's it holds the byte number 4 and 5. Thus the next memory address can only start from the byte number 6. Indeed, we did start from the 8th byte for this counter. In the PV, we are going to enter the number of boxes to be removed to put back the counter in its initial value, hence turning on the output, which in turn deactivates the motor as a sequence of the process. Now we are done with almost all the conditions. It remains to put them in the right place. To stop the motor for a period of time, we use a closed contact before the motor and assign it with the timer's address. We stop the motor until an other start, either by a press on the stop push button or the counter down output. Thus, we drag 2 contacts to the reset and assign them with the stop push button and the third memory address, which retrieves the counter down output. The program as it is seems to be complete, however there are hidden conditions that do not appear when we are given the step-by-step process. To complete the program we need to reset the count up counter. Well, we use an open contact and assign it with the timer's address, since the timer start coincides with the counter when it reaches the required boxes. As to the countdown counter, we need to reload the preset value. Ideally, we make the start push button seeing the fact that the counter output deactivates the process. So, at each start the preset value is loaded. However, beware this remains valid in a perfect environment with no failures altering the process such as power failures that would reinitialize the counter. In this case, other considerations and parameters will enter to the game which are out of the purpose of this course. Well, we compile the program then we move to simulation. For those who try for the first time the simulation of the 1500 PLCs, it's a bit different from the 300 and 400, we all need to do is following the steps. Errors might occur at the level of the connection interface, software compatibility that a PLC professional needs to handle carefully as it is part of industrial control systems journey. Once the connection is established between TIA portal and PLC Sim, we create a simulation project in PLC Sim to complete the loading of the program. We open the Sim table and wait until the final step of program loading is fully complete. As shown here, the variables show up directly. This is a sign that the connection between the two software was established right. For a tidy simulation, better we enter the variables by order they perform the process sequences. We change the representation format to decimal for box number to see clearly the current values of the counters. Moreover, make sure to enable the modification of variables at the first simulation launch. Now everything is ready to start, just we click on Run. It's noteworthy to stress out that the visualization is optional to run the simulation, nonetheless it's necessary to check program errors during simulation. We press on the Start push button. Normally we see the motor and the green indicator light active. We simulate the detection of the small boxes on the conveyor by activating and deactivating the first sensor. As we see the box number increments at each signal from the sensor. The timer started and the motor stopped for 5 seconds when the counter reaches 5. That's 5 small boxes detected. However, there is a missing sequence. The blue indicator light is supposed to flicker while the timer is running. We stop PLC Sim and check the program to find the error. Probably it's about the counter reset. Indeed. The timer as used here will actually reset the counter but can't turn on the blue indicator light. Since we need the blue indicator light to flicker during the timer is running, we will have to use a negative edge bearing the timer's address. Could we load the modification and simulate to see how it works? Well, we do the same as the first simulation. We start the motor, then we simulate the detection of the small boxes by the first sensor. As expected, when the counter reaches 5, the blue indicator light starts flashing, the motor and the green indicator light stop for 5 seconds. We simulate again, but this time we include the second sensor. Actually, the process as it simulate, we did not take into consideration the number of small boxes the big box should take to be removed, otherwise the count up and count down counters would have preset values on this basis. As we can see, the counter decrements at each signal received by the sensor. The program seems to run as it should. As it's been shown, the motor stopped when the down counter reaches 0, meaning that 7 boxes are removed. Moreover, at each new motor start, the number 7 is reloaded to the counter. Hope that everything is clear. For any further clarification, or some that you have not realized fully, let us know in the comments. Now, if you find the video interesting in some way, make sure to give us a like and subscribe to the channel. See you in another video.